So, okay, so today my objective is just to entertain you after dinner, I hope, and to explain you several aspects of my research based on some examples. So probably my first slide is going to be the most mathematical one, but you will see then why I'm doing so. So, of course, we are mathematicians, so some equations. But let me explain you briefly what this means, because it's not that complicated. So here, what we have are m particles that and I'm following the position of the particle, which is given by xi. And I'm assuming that they interact between each other, like we are interacting in this room, some sense. And there is a potential of interaction between the positions of these particles, between quotes. And this potential is where all the modeling enters, which is called U. So somehow this part here is giving you the sum of all the interactions between all the particles, xi, that are felt by the presence of the other particles, xj. So this is what this means. And then what this dot is that I'm saying that the rate of change of the movement of that particle is going to be given by that sum of the interactions. Okay, this is a very simple rule of movement of the particles, which is very interesting because it's as simple as it is. It leads to very complicated patterns. So this is where the fun starts, and you say, okay, so I'm gonna simulate 200 particles chosen at random in the square. I'm gonna follow their movement through that law, different kind of functions, this potential U that was appearing there. It doesn't really matter the shape of the right-hand side of that system that I showed you before, but you can see that you can trust me, with very simple functions U, you can get very complicated patterns for the location of those positions, okay? That you cannot guess just for the shape, from the shape of the potential, the function U that was appearing in that formula before. Okay, so what this has to do with any applications? Are you just having fun? Okay, so let me mention you one of the first applications that triggered my attention to this kind of questions, which is related to the movement of bacteria of cells by chemotaxis. This is a model that was introduced at the beginning of the 70s by biologists, not by mathematicians. And what they were trying to explain is the movement of cells on a Petri dish, because they were playing this kind of experiments. Here you have how many? 7 cells. And then there is somebody that arrives with a pipette and puts some chemical substance over there. And you see that the cells, they are directing their movement immediately towards the source of this chemoattractant. So they are able to feel the change of the chemoattractant concentration, and then they direct their movement towards that location. So this formula here is just an expression. Well, it could be complicated. I don't have to explain it to you what it means, really. But it's an expression, a mathematical expression of that. The cells are trying to move in the direction of the gradient of the concentration, which is this term over here. And at the same time, the cells are diffusing. And this part means that the cells, in fact, this model in particular is not exactly what is happening here, but this model, what it means is that the cells are producing that chemical substance to which they are attracted to. So what is this model about? Here we have 8 cells. N means the probability of finding cells at a certain location, or the number of cells at a certain location. So this is what is called a macroscopic model, meaning that it's a model for not for 8 cells, but for 10 to the 8, 10 to the 9 cells, when you want to explain the movement of the overall movement of the cells. Okay, so this is just an example of what is called collective behavior models. And just to give you an idea what it means particle for me, and I put particles between quotes. Particles means whatever it has to mean in the particular application. So the classical application of this theory is for rarefied gases. If you look at the upper atmosphere, then the gases there are very rarefied, very few molecules, and this kind of modeling makes sense. And then the particles are gas molecules. If you are in different applications, and here I'm just listing several of the applications that have been done with this perspective, you have the particular application field, and what it means really is particle in that kind of application. So I'm going to give you a couple of more examples on this. And the next one I'm going to give you is about swarming, because it's always interesting. And we are talking about social distance and about the 2 meters rule, okay? So we will understand very soon why I'm saying that. But let me just mention that this kind of modeling comes from a very basic question that the famous German mathematician Hilbert posed already in the first International Congress of Mathematicians in Paris in 1900. He was asking, how can you obtain the fundamental equations of fluid mechanics from basic Newton's law? If you just think that the air in this room is full of 10 to the 23 Avogadro number times I don't know how many more, and then you are following each of the molecules with Newton's law. How can I get the fluid equations out of the Newton's law of each of the molecules in this room? So that's the kind of question he posed, but this is very much a question that you can apply to many other fields. So this is always fun. So here you have some examples of swarming in animals. And here you have a particular case of a fish show that you have seen in all David Attenborough TV documentaries in the BBC many times. We don't have the dolphins here coming by, but that's the typical thing. You see this kind of collective behavior of the whole fish show. And what you want to explain is why they produce this kind of coherent structures just by the interaction between the individuals. How do they count that they can synchronize their movement? How do they count that they do something together? So here we go, social distance. Okay? So let's assume a very basic model. And the very basic model assumes that the particles, say the birds, they don't want to collide. So they have some area, comfort area. They want to be far away from the people, not too close, the 2 meter distance. Okay? But the people are social. They want to be together. So there is an attraction. And also, you can assume that there is a tendency to follow or to mimic the behavior of others in the group. So some kind of alignment, whatever it means here, this alignment. So can we explain the behavior with this collective behavior with these very simple rules? So this is a line of research in which I worked in the past and still work now with different directions, but I'm going to show you one of the basic models that was proposed some time ago. So these models is based on Newton's law. So, one thing I learned when I moved to the UK is that Newton is my only god now. Okay, so Newton has to be in all my slides. So, of course, it has appeared already twice, if you realized. So there was a statue of Newton before in Cambridge. Anyhow, so these are kind of Newton's law. Again, you have this potential, which is, in fact, is where I'm going to introduce the attraction-repulsion between the individuals. So with the choice that I have here, if the function, as a function of the distance, is decreasing, this force is repulsive. If the function is increasing, this force is attractive. So this potential means that if I'm very close to you, I prefer to separate from you. If I am at a distance larger than this, I prefer to get closer to you. Okay? So this is what it means, and this is what it does, the sum of all the interactions between all the individuals that are here. Okay, here is just a term that is fixing the cruise speed of the individuals. Asymptotically, they want to go to certain speed. When we walk in the street, maybe we go to a certain fixed speed. Okay, so it's just the role of that. Well, it's an example of the potentials that was over there. I don't want to make too much of emphasis on that. Let me get to some movies here again for the simulation. And here, you're going to see that in this very simple model, which has just attraction and repulsion, nothing else, not even some kind of a behavior of alignment, all of a sudden here, you see that the particles, they arrive to a consensus in the direction they want to move. The arrows are the velocities. The points are the positions. They are moving in this direction, but just to follow them, I'm centering the screen at the center of mass of all the particles, okay? So this means that they are moving with this shape in this direction. It's what we usually call a flock profile, because they flock with certain shape. Here, from when I started, nothing has changed. It looks like they are doing something random, chaotic, but you will see very soon that's not the case. In fact, it's starting now, and then just after a few moments, then you see that they are turning around certain locations to what we call a milling profile. Again, with certain distance, fixed by the rules that you impose. So interesting things like this happen in all these kind of dynamical systems. And you want to explain what are the qualitative properties of those evolutions to predict if this is going to happen, how it's going to happen, and in which way it's going to happen. So let me show you another application of these ideas. This is a kind of novel application I've been interested in very lately, and it's about a very general scientific question that if I would know how to solve it very efficiently, I would be at Google and not here. Meaning that I want to minimize a function. But I want to minimize a function that has a unique global minimum. I want the global minimum of that function, and I want to compute it efficiently. And no matter how many dimensions I want. So I would like to do it in high dimensions. Okay, so this is just a function that I want to minimize, the shape of that function. It has lots of local minima, but do only one global minima here. And here I'm going to show you one method to minimize a function based on agents, which are kind of explorers that they go in the shape of the function here. Oops. Let me see if this one wants to work. Yep. So let me see if it works again. So what you have there is the trace of the particles that are moving and looking for the location of the global minima. What here is a kind of a consensus model. They exchange information about where they are in terms of what they see or what they measure, and then they move towards the direction, in this case, of the trying to find the global minimum. And I'm going to enter in any details there, just to give you an idea of the kind of applications. And in the few minutes left, let me show you other interesting phenomena that may show up in this kind of models. I'm going to use as an example a life sciences model, a life sciences problem in which you want to model segregation. Let me show you what do I mean by this. This is an experiment done by some collaborators in a biology department in Japan, in which what they did is to grow colonies of certain cells that had been genetically engineered in such a way that you can change the level of expression of certain proteins. By changing the level of expression of certain proteins, they are able to modify the ability to adhere to either the red cells or between the green cells between themselves. Originally, they are the same. And here in this experiment, when they grow, you see when they grow, they meet, and they meet in a front that is perfect. There is no deviation between them because they are the same kind of cell. So essentially, they have the same properties. Here, the green cells have been genetically engineered, by changing the ability to adhere to the green or between the greens or to the red. And then you see that there is an intermingling zone here. There is a kind of area in which they are mixed. There is an invasion. Okay, how can you model this? Okay, so here what we did is a kind of model based on this idea. So we had like two types of cells here and just with different colors, yellow and black. And then again, I'm assuming certain interactions between the yellows and the black. So probably in these potentials, I can introduce things like the yellow like the black, but the black maybe they don't like the yellows. Love is not bidirectional sometimes, so it depends. So you can put attraction, repulsion effects between the different kind of particles. And you can introduce the different type of interactions at the microscopic level. If you do this kind of procedure, this procedure that I showed you some ODs before, in which you are able to obtain some kind of macroscopic equation, you're able to write some PDEs for the evolution. Oops. Let's hope that this works. Good. Nice. So these are the PDEs that I'm not going to explain again from where they come. But the interesting thing is that here is the experiment. This is a real experiment. The same experiment on live as I showed you in the previous slide. The cells, when they are at the same time, they meet in a perfect front. When they are of different type, there's an invasion. So the model introduces the differential adhesion by putting different strands of the possible interactions between the different type of cells. And the model is able to capture precisely, this is like a vertical cut, a horizontal cut here, in which I'm modeling these PDEs. I'm solving these PDEs. I'm not doing any experiment. This is the real PDE with parameters that have been fixed from the experiment. And then let me run it again, if I can. Yeah, oops, yeah. So that's the experiment. Let's see if I get the experiment running. The experiment and the simulations. And you see that one captures this behavior that when they meet, there is no, they are segregated here, there is some mixing, and you capture somehow the length of the mixing here. And here you have the different kind of behaviors that can happen with a random initial data, again, in 2 dimensions with that kind of model. The same initial data for each of them, just changing one parameter in the model. You can go from this that is a kind of mixing between the two types of cells to something in which one of them is surrounded the other type of population. And here they are separating, and finally they are segregated. So this kind of complicated phenomena can happen with very simple, at the end of the day, that system of PDEs here, partial differential equations, is not that complicated and is able to capture all these kind of different phenomena. So with this, I think this is more or less what I wanted to tell you, because I think I'm almost over time. And just to tell you as a conclusion that, let me see if I can continue here now. Yeah, let me just jump to the conclusions. That agent-based modeling, which is our particle systems, is a very interesting, from my perspective, powerful technique that you can use to go from micro scales to macro scales in many different applications. And in this kind of models, there are equations that are called aggregation-diffusion equations, which are the ones that I showed you, and kinetic models, which have different approximations, and all of them, they are the natural PDE continuum descriptions that can be used to simplify the computations and use in practice. Also, from the pure mathematical point of view, they are beautiful, at least to me. Even if you don't understand the gradient and the Laplacian or the divergence, they are beautiful to me in the sense that they are so simple and can have these complicated structures, and then understanding their properties is really what I'm trying to do. And at the end of the day, what we would like to know are qualitative properties of those models. What can we say about the typical behavior when t goes to infinity? What can we say about the steady states, the stationary behavior, and all these kind of things? And thank you very much for your attention.